Hey students, we're starting our unit on mechanisms, so we're going to start with simple machines. Let me switch it over here to the presentation. So there's 6 simple machines, all right, and you've encountered these in your life. And the whole purpose of these simple machines is to do work, okay? And we'll talk about that in a little bit. But basically, they are going to change um, the amount of force needed over a certain distance. That's work. So I'm going to divide this up into two different presentations or lectures. We're going to talk about these three first: the lever, the wheel and axle, and the pulley, and then I will break it into um, a different video, and we'll do the incline plane, the wedge, and the screw. And these are all very familiar to you in your Gateway to Technology classes. You should have covered this. We'll go over it quickly, but we're going to start to put some math to these concepts and start to predict and explain the things that we see around us based upon what we calculate. Okay, so we're going to introduce you to this idea of what's called mechanical advantage. And if you look at the definition, it can get really scary really quick. And it's something as you pursue engineering, you need to not be scared of. It's just a certain way of describing a mathematical formula. So mechanical advantage is the ratio, all right, so we know we're going to have something divided by something else. Ratio of the magnitude of the resistance and effort forces, okay? So we're going to know the mechanical advantage is if I am, trying to lift something, right? I am pulling down and at the same time, gravity is pulling it. I'm lifting up, and the gravity is pulling it down. We also define mechanical advantage as the ratio of distance traveled by the effort and the resistance force. Okay, and we are interested in this. We are doing this because it allows engineers, in this case, they're saying designers, someone who's putting together a new product to manipulate speed, distance, force, and function. Okay, if you think of, if you think of, when we do VEX, sometimes we need to lift something really heavy. All right, and so we want the motor to turn many times and slowly lift that up. That's kind of the trade-off that we do. Or sometimes we want to hurl a ball like a catapult, so we want to quickly release that energy and trade speed for lower torque. All right, so I can't throw something quite as heavy. All right, so mechanical advantage, when we talk about it in words like this, it doesn't make a whole lot of sense. So let's think about it. Let's think about it just kind of from a a picture point of view. So if we look at this inclined plane here, right, we're doing a certain amount of work, which is we're lifting the block a certain distance off the ground. And if you see those arrows, those are force vectors. All right, because they have a magnitude, right? I'm lifting it up, I'm pushing down. The block weighs, 1 pound, right? And it needs 1 pound of force to lift it up. So if you look at the force vectors here, and they have, by a vector, they also have a direction. So they have a force, I'm pushing down with 5 pounds, and I also have a direction, down. Okay, this is I'm lifting, 5 pounds, and I'm moving that up. Okay, so what mechanical advantage does, so I'm doing a set piece of work, right? I'm lifting this block. All right, mechanical advantage allows us to to make it easier or harder depending on what we want. Okay, so as this block, right, as we push it up, notice your little force vector here, right? The force vector is less, right? But if you look at this force vector, you'll notice that the block is still exerting the same amount of force down. Okay, so it's still gravity. The block still weighs 5 pounds, right? But because we are using this ramp to create mechanical advantage, as it slides up the ramp, right, we're doing work over a longer period of time, so we need less force because ultimately we need the same amount of force. All right, so if I lift that block straight up, right, I'm going to need more force. Okay, engineers use this because maybe we don't have a motor, right? We don't want to purchase a more expensive motor that can lift directly straight up 5 pounds. Okay, we know we have plenty of time, so we're going to trade time because it's going to take longer to slide. Notice this block gets up there first, right? We're going to trade time for a less expensive, a less powerful motor, and then use a ramp to give us mechanical advantage. All right, so we don't have to do, we could do not all of the work all at once. Okay, and so when we talk about mechanical advantage, we express it as a ratio. So this has a mechanical advantage of 4 to 1. All right, and in this case, the effort force, all right, this little red arrow here, is 4 times less than the magnitude of the resistance force. All right, so if we're saying this is 5 pounds, right, then I would need to do this example, I would need a motor that could lift 5 pounds. However, if I incorporate an inclined plane to my design, then I only need a motor that can lift 5 pounds divided by 4 because it's 4 times less. And that's what 1.25. So I could get a motor that could lift 1.25 pounds. All right. And I've just talked about this. We're trading, right? We're trading the distance, time. The effort force is going to travel a much longer distance than the resistance force. Okay. So that brings us to the concept of work. Okay, and so the whole point of these of mechanical advantage, the whole point of using a simple machine is to do work. Okay, and work is simply force that's applied over a distance. Okay, now when you get into physics, which is kind of what we're talking about, we always want to set up boundaries, okay? And in the course of this, the boundary that we're setting up is the distance the object travels parallel to the force, okay? So if the force is coming this way, right, we are measuring the distance that is parallel as well, right? So parallel to the force. And that's why they add these little parallel lines here. All right, so that's distance parallel. It's just to help us remember, all right, that work is force times distance. And then we add those little parallel lines to indicate, okay, it's the distance parallel, okay? So I've also talked about this, but I just want to hit it one more time. So when you're doing work, you the it's the same regardless of your mechanical advantage. In the case of the lifting block, we are lifting, because remember, it's force times distance. I'm lifting 5 pounds, right? And it's parallel to the force that is exerted, right? So I'm lifting 5 pounds, 1 foot. Okay. In the case of this, I am still lifting 5 pounds, and the force parallel to that force, or the distance parallel to that force, is still the same 1 foot. Okay, so I'm doing the same amount of work. Whether I lift it straight up or I slide it along an inclined plane, it's still the same amount of work. Okay, because we're not measuring the distance along that inclined plane when we think about work, because what our previous slide is, right? We're looking at the force times the distance that is parallel, right? And if we're going up an inclined plane, that's not going to be parallel. Okay, so just keep that in mind. Okay, um, so here's something handy to write in your engineering notebook. Um, where 1 is the magic number. If it's above 1, something has happened. If it's below 1, something has happened. Okay, so if mechanical advantage is larger than 1, bigger than 1, you're gaining mechanical advantage. You are using less force to accomplish your work. Okay, if mechanical advantage is less than 1, then you are using more force to accomplish your work. Right? And there's a trade-off, right? If mechanical advantage is less than 1, so I'm using less force, right? I still have to do the same amount of work, so therefore I'm going to do more, I'm going to apply effort over a longer distance. Okay? If mechanical advantage is less than 1, right, I'm going to need more force, but I also require less distance. Okay? And you can think of this as like a crowbar, right? If I put my crowbar, if I arrange it one way, I can lift a boulder, right? But if I move the fulcrum point, the part that it's rotating around, closer to my hand, right, then I could suddenly not be able to lift a toddler. Okay, because I'm changing that mechanical advantage as I move my fulcrum point. All right, mechanical advantage, because it's ratio, and you're going to have some number divided by some other number, it will never be less than or equal to 0. So you will never get a negative number. You will never get exactly 0. If you do, your math is wrong. Okay, so that can be a quick check for you. I'd probably put that in my engineering notebook, like, hey, all right, if I get 0 or a negative number, I've typed something wrong. All right, and to go back and look at it. Okay, so there's 2 calculations that we do when we talk about mechanical advantage. We have ideal mechanical advantage, and that's basically just a perfect world. All right, it's just theory. We're not looking at things like friction. Okay, we're just saying everything's perfect and frictionless. Right, friction being, if I put my hand down on a desk and I push down, right, my hand doesn't want to slide. Right? If I put that on sandpaper, it really doesn't want to slide. Right? If I'm down on a wet countertop, right, it's going to have less friction. All right? So friction is the effort that's required to move against another surface. Right? So in ideal mechanical advantage, you don't think about that. It's simply we assume that it's frictionless, and we get, in a best case scenario, in an ideal, that's hard to say, in an ideal world, right, this is the best it could ever be. All right, and so that is basically, all right, your distance traveled by effort, so that DE, all right, your effort force, and divided by the distance traveled by the resistance force. Okay, because remember, we're talking about, like, we have a resistance force, and that's the ultimately the work that we are doing, right? And we're trading. When we look at mechanical advantage, we're just trading distance, and some people like to think of it as time. We're trading distance for less effort. Right, we're still doing the same amount of effort, right? But our force is less. Okay, so take a second, write that down in your engineering notebook. IMA, ideal mechanical advantage, and I'd probably write ideal mechanical advantage so you don't forget. All right, and then I would write DE over dr, and I'm doing that right now as I'm talking. All right, and then I would label that DE equals distance traveled by effort force divided by dr, distance traveled by resistance force. So take a second, pause the video, and write that out in your engineering notebook. You're going to use it again for several days. Okay, the other one we're going to look at is actual mechanical advantage. So AMA. All right, and it's a little bit different in that we get this calculation through experimentation. So that's what it means by inquiry-based calculation. We built a mechanical device, and now we are measuring the forces. Okay, and when we do that, we get the frictional losses in there. Right, we get the friction loss of, the two parts don't want to rotate. Without a little extra force being added in, right? Think about, when you're starting your bicycle. There's a little friction there to get started. Okay. If you ever see a problem, this third thing used in efficiency calculations, if you see a problem, it says how efficient is it, right? It wants you to use the AMA. Okay. And it's basically the ratio of the force magnitude. So AMA equals F force of the resistance divided by force of effort, right? And the mathematically inclined of you are probably noticing that this is FR over FE, resistance over effort, and the one before was effort over resistance. So we've kind of taken the inverse of this, okay? So go ahead and write that down, label what is what, okay? So actual mechanical advantage, and write that down because you're not going to remember what AMA is. So AMA, actual mechanical advantage, is the resistance force over the effort force. Okay, and that's actually how I like to say it. I like to say the little r first, resistance force, right, then force resistance. Both are perfectly correct. It just makes more sense in my brain to say resistance force. Okay. So, here's a part where you can pause the video, okay? Can you think of a machine that has a mechanical advantage greater than 1? So we want to take something that's taking a very light force, all right? A very light force, and then using that light force over a long period of time to do some work. So take a second and think of that. So there's many thousands of combinations that you could have come up with, but a windmill is a good example, right? We have these turbine blades. They probably each weigh like 500 pounds apiece, right? And we have the wind blowing at a very light 2 to 3 pounds. Now, to be honest, right, the blades are big. The wind is blowing over the entirety of the blade, so we may get 1 pound per square inch, and it's got a lot of square inches, right? But we take these giant blades, right, and they want to harness as much energy as possible, right, and they're really long, right, and then as the wind hits that blade, the airfoil causes a force to be exerted in a circular motion, which makes them turn, right? And we have this really long blade turning a very small diameter axle, right? And so this has a mechanical advantage much greater than 1. It's probably in the 500-600, okay? So, can you think of a machine that has a mechanical advantage less than 1? So in this case, we want to put forth more effort and get a lot more distance. So take a second and think about it. All right. In this case, and again, you could do thousands, right? Some weight machines are like this, right? I want to do the plates be 30 pounds, right? But I want to be lifting, the equivalent of 100 pounds, right? So therefore, my machine doesn't need 1,000 pounds of weight to move, for me to move 1,000 pounds of force, right? If I'm doing like a leg a leg press, like an angled leg press, right? So I could design in a mechanical advantage less than 1 to say, all right, I can take a 50-pound plate, I can make it 1 to 2, okay? So as I move, right, a very short distance, my 50-pound plate feels like 100 pounds. All right. So one of the things we're talking about, if we look back at the title of this video, we're looking at the lever, the wheel and axle, and the pulley. All right, so we're going to break into half of the simple machines. So we have the lever. Okay, so rigid bar exerts a pressure point, and if you've ever used, a crowbar, you've used a lever. All right, so you have a weight at one point, and you apply force somewhere else, and then there's a fulcrum, and that's the place it pivots around. Okay, so and there's 3 different kinds of levers, and you can kind of see those there, and let's talk about them. All right. Okay, in a first class lever, and I would take some notes on this, the fulcrum is located between effort and resistance forces. All right, so it's in the middle. Okay, so effort and resistance forces are applied to the lever in the same direction. So this is your classic, I have a boulder, the resistance force, I am pushing down on the end of the bar, and in the middle where it touches the ground, where the bar touches the ground, is my fulcrum point, right? And if I'm moving a boulder, right, I want to move this fulcrum point as far over as I can and as close to that boulder, right? So therefore, I can use less effort to move the boulder a smaller distance, right? And that's what we're doing here, right? I'm sorry, that's what we're doing here, right? Because we're looking for a mechanical advantage bigger than 1. So my effort is here, my fulcrum is close to my resistance, and that gives me more leverage, right? More mechanical advantage to move that boulder, okay? This is the only lever class that can have a mechanical advantage greater than or less than 1. It all depends on where you put your fulcrum, right? In the case of this one, I'm putting my fulcrum close to my effort. Why, Mr. D, would you want to do that? Maybe I have a ball here. I put my fulcrum here, right? And then I want to slam my hand down on the table, right, causing the ball to fly into the air at a great speed, right? So I can trade using a whole lot of effort, slamming my hand down, right, with my fulcrum close to my hand, right? So I do my effort close to my fulcrum, and then that causes the ball to much lighter ball. I couldn't do that with a boulder, right? I would just hurt my hand. But if it's a light little foil ball, it's going to go flying into the air, right? So that would be why I would want to do that. Okay, second class lever. All right, again, take some notes. Fulcrum is located at one end of the lever. So you'll see the fulcrum is at one end. Resistance force is located in the middle, all right, and then I'm pulling up on the end. Okay, in this case, the resistance force and the effort force are in opposing directions because it doesn't work otherwise. Think about it for a second. And this is your classic wheelbarrow, okay? Right? If the one we just looked at, the first class level is your crowbar, this is your wheelbarrow, right? Think of the fulcrum, the part you're rotating around is the wheel. If I do this, right, I can see, oh yeah, right? I put my load in the middle, and then I pick up on this end. Okay, this always, why do we have wheelbarrows? Because I normally can't carry 500 pounds of gravel. I put it in a wheelbarrow, I can move 500 pounds of gravel, right, someplace else on the construction site. Okay, so it always has a mechanical advantage more than 1. I am always trading a little bit of effort. Right, it doesn't take me much to pick up the end of the wheelbarrow, but now until I'm done moving, I've got to hold it. Right, so I'm holding it for a longer distance, right, as I move it around. And then the third class lever, all right, the fulcrum is located again at one end, right? The effort where I'm pushing is located in the middle, and the resistance is in the other end. Okay, it's always a mechanical advantage less than 1. right? Because when I pull here, I'm not going to pull with as much force as when I'm over here. Mechanically advantage. All right, I could apply the same amount of force, right? But it's going to take more effort to pull from the middle than it would if I was pulling down here. All right. This is always the hard one to visualize. Like, I don't see this in the real world, Mr. D. You do, right? Your car door. Okay. The car door has weight all along the edges. It's usually heavier on this side because it's got the thickness of the door and the latch. And then you grab it in the middle and pull your car door shut. All right. So that's a good way to visualize the third class lever. Okay. Now, a few more engineering terms. Okay, we have a moment. Okay, and so a moment's the turning effect of a force about a point. All right, and then they get real math related, but don't get scared. Equal to the magnitude of the force times the perpendicular distance from the point to the line of action from the force. Okay, basically what they are saying. Let's see if it has a picture. All right, so so they just represented what they just said, right? And that seemed like super scary. All right, that was like, Mr. D, I don't understand that at all. But all they're trying to do is put into words an equation. All right, so we have a moment, and that's equal to the distance times the force. Okay, now it is perpendicular. All right, so at a right angle. Okay, but moment is just distance times force. Okay, as long as you choose the one that's at a right angle. All right. Um, and that a moment is just that turning force. If I'm pushing here, right, I am creating a turning force between this point because I'm trying to turn around that point and here, right? And the longer that gets, right, the more moment, the more the larger moment I am creating. All right. And we also use the word torque. Right. You see torque wrenches. Right. You see apply more torque, and it's basically just a force that produces a rotation or a torsion. All right. So, and all that means is it's rotating. Right. If this is attached here at this fulcrum, right, and I push down here, right, it's going to create a torque around this point. Right. It's going to want to lift this up. Right. And so I will get a rotational force, right, around that point. Okay, and we can do some calculations on this, right? So we just said it's distance times force, all right? Simple pre-algebra, okay? So calculate the effort moment acting upon the lever. So we said distance times force. Effort moment, right? Distance, 5.5 inches, times force, 15 pounds. And so moment is distance times force. Effort moment equals 5.5 times 15, which means I have, now, here's the key. You cannot drop your units. All right, so I have 5 inches, oops, and 15 pounds. So I end up with 82.5 inch-pounds, and that's how you say it. Okay, it's not divided by it, all right, because we're multiplying it together. They just get they get multiplied together. 82.5 inch-pounds. Right, and if you are familiar with torque wrenches, right, you can get them in foot-pounds. You can get those in inch-pounds. Okay, so it's pretty standard if you're in the non-metric, freedom units. Okay, then we're starting to get a little bit deeper into this. Okay, when all your moments equal 0, okay, it's not moving. And let's switch over to this. Okay, so I'll pull this back. So here's my lever, right? I can get it to a part, maybe, right, where all of my moments equal 0, right? And that's all they mean by equilibrium. Okay, I have it balanced, right? The force right? Again, because it's force times distance. So the force being exerted from, so here's my fulcrum, the force being exerted on this side that's pushing it down this way, right? Which makes this end want to move up. Oops, you can't see that. Which makes this end want to move up, is equal to the force, right, pushing down here times this distance, right? And so I get a balance. If, right, I unbalance it, right, so now my force times my distance, right, is no longer in balance, what's going to happen, right? I get a moment, and it rotates off my finger. So if I'm out of balance, all right, I get a moment, it rotates off my finger. If I'm balanced, right, then if we go back to here, and that is, what button is that? That one? Nope, that one. All right, so if it's in rotational equilibrium, it just means all things equal. It's balanced on both sides. All right, so all of the clockwise moments equals all of the counterclockwise moments. All right, and before you get bent out of shape, right, all we're talking about is if this is balanced, right, then I don't have anything trying to spin it off my finger this way. I don't have anything trying to spin it off my finger this way, right? It's balanced, right? If I apply too much, then it's going to fall off. It's no longer in equilibrium. So we can use this to do some calculations, right? Using what you know regarding rotational equilibrium, calculate the unknown distance from the fulcrum to the resistance force, okay? So now we're going to do a little bit more advanced math, right? We have a single unknown, right? I can figure out the moment on this side, 15 pounds times 5.5, 15 pounds times 5.5, equals, that's your fulcrum, your equal sign, right? Because it's on the other side, all right? 32 and 2/3 pounds, okay? I would probably change this in my calculator. I would enter 2 divided by 3 and change, and then my calculator is going to say 0.66666666, all right? And I would rewrite this 36.66, okay? And that's what I did here, right? Times, oh, wait a minute, I don't know this distance. All right, times some distance. And now it's a simple algebra problem that you solved like 100 times before, right? 82.5 inch-pounds equals 36.66 pounds times the distance of the resistance, right? And then you just do the math. Okay, I need to take this over to the other side, so that means I divide by 36.6, and when I put that in my calculator, I get 2.25 inches, right? And if you keep track, right, this pounds cancels, this pounds canceled, what am I left with? Just inches. Okay, so the important part here is all the things on one side of the fulcrum that's trying to send it counterclockwise has to equal everything on the other side of the fulcrum that's sending it clockwise. Okay, so in this case, this effort has to equal resistance. All right. Otherwise, it's going to do like I see in the picture where it just flies off into space. Okay. And that's kind of what I was talking about, right? If you don't, if they don't equal out, right? If they're not opposed, if they're not equaled out, then these are going to travel in a circle, right? If I push down here with 10 pounds and I push down here with 5, right? Even if this was straight in the middle, so you would think, all right, if the forces were equal, they would balance, right? Think of a balance beam, right? But in this case, I have a whole lot of effort force getting put in, and I also have a much greater distance, right, than here, right? What's going to happen is this is going to swing around this way, right? Because I am not balanced. So I'm not in equilibrium. I'm not static, right? So as this is moving around and around and around, right, it's going to, if I put a point If I drew a point, had a marker on the end of this and watched it go around, it's going to follow that circle. And the same thing here, right? If I'm moving this one around this way, all right, and this one is going to move around this way, right, on that circle. Okay, so you could use this to your advantage. All right. Circumference is the distance around the perimeter of a circle. All right, and so all this is reminding me is, right, this is 2 pi r, right? I don't know why that doesn't say pi, but it should be 2 pi r. Circumference is 2 pi times the radius. Okay, so if you're looking at ideal mechanical advantage, right, it's going to be 2 pi over 2 pi. Those cancel, so really all you have to do is how long is this arm divided by how long is this arm. Okay. So that was IMA, and I would take a second and write that down. IMA, all right, IMA equals effort arm length divided by resistance arm length. All right, because now we're going to go and do AMA. So AMA, ratio of applied resistance force to applied effort force. So AMA, same as before, right? So you already have this written down, FR over FE, and I'm writing it again. All right. So what is the AMA of the lever above? Okay, so we need the force of the resistance divided by the force of the effort. So we have 16 times 5.5, distance times force on this side. So this is on the effort, so that's going to be in the bottom. So whatever that number comes out to be, and then 2.25 times 32, and that's going to be on your top number. So I think, right, 32, those pounds cancel. Okay, so they're just looking at the forces. I got that slightly wrong there. So we have 32 on one side. Oh, because it's already solved out. Duh. Okay, so in this case, AMA, force of the resistance, right? Because they're already giving it to us. We don't have to calculate it. That's where I got confused, right? Force to the effort. So 32 divided by 16, 32 over 16 gives us an AMA, actual mechanical advantage, of 2 to 1, right? And that was if we measured it. Okay, that was as if we measured it. The part where I got confused on is normally we have to calculate one of these. So that's where I got confused. So in this case, if they're already giving you what the FR and FE is, just plug them in, right? And then we have distance effort over distance of resistance. So we have the distance here, all right, because so they're giving you everything. Normally I leave something blank and you got to calculate it, all right? So 5.5 over 2.5, all right? So the ideal mechanical advantage in a super perfect world, all right, it would be 2.44 over 1. And you'll notice, right, IMA, it should always be higher than the AMA, right? Because, right, this is actual, includes frictions, and so we're going to have a little bit of loss. In this case, 0.44 is lost of our advantage due to friction, right, from trying to turn around this point through slicing through the air. Okay. Oh, and I just answered my question. Okay, so if we have this calculated, right, if we know AMA and we know IMA, so actual and ideal, then we can calculate how efficient it is. Okay, so I would write this down too. Efficiency, right, is how much of, in a perfect world, if I could get this, how much do I really, exert, right? If my ideally I should get 100, right, but actually I only get 50, right, then if I'm only getting half of what I ideally should get, then I'm only 50% efficient. All right. So how efficient am I? So what they do is percent efficiency equals AMA, actual over ideal, times 100. Right. The times 100 is just moving the decimal place 2 places, because when you deal with percentages, it always comes out as like 0.27, right? 27%. So if you divided this out, 2 divided by 2.44, you would get 0.82 on your calculator, and they're just moving the decimal place 2 by multiplying it by 100. See those two zeros, so you get 82% efficient. Okay. So if we go back to the previous slide, what is the efficiency of that lever, right? So we want to do AMA efficiency. And let me switch to this, right? So we want to do efficiency, percent efficiency, right, equals AMA over IMA times 100. And if we go back to the slide before, our AMA was 2, and her IMA equals 2.44, right? And we would divide that out. And then multiply it times 100. And if we did that, let me pull up my calculator. So 2 divided by 2.44, that gets us 0.1 or 0.819. Multiply that times 100, or move the decimal place in your head. We get 81.967. So we can round that up to 81. The 9 is going to round up. We can just round that up to 82.0. All right, so that was 82% efficient. And let's switch back to this picture. So there's my calculator. All right, the 9, the 6 rounds up the 9 to 0, and then that's going to be the 82. Okay, it is important to realize that no machine is 100% efficient, because there's always friction losses. That's the way our universe is set up. If you get 100 or higher, you are violating the laws of the universe. You've done a math error, okay? If we could truly have a machine that was more than 100% efficient, it would be a perpetual motion machine, and it would create free energy, which breaks the laws of the universe. Okay, so wheel and axle is the second one. A wheel is just a lever arm that's on a shaft. Okay, the shaft is called the axle. They move together as a simple lever. All right, to lift or move an item by rolling around. It's the only thing you have to think about is which is applying the effort and which is applying the resistance force. Okay, is the effort coming from the axle? Is the axle being turned, right? Or is the wheel being turned, therefore driving the axle? That's really the only tricky part of dealing with this. The rest of the time, it's just a lever. All right. Can you think of an example of a wheel driving an axle, right? The way it works in a car is the motor turns the drive shaft, which turns the axle, which makes our wheels turn, which makes our car go. The reverse of that, have we ever seen a pulley or a garden hose bib or the knob on our oven? Okay, that's where we have a wheel that we turn an axle on the inside. Okay, and this works out pretty easily too. All right, both the effort and resistance forces will travel in a circle if they're not equally or unopposed. All right, that's how our cars go. Our IMA, all right, it's just the same as before. You don't have to write this down because you already have DE over DR written in your notes. All right, so it's 2 pi r. All right, but the pi's cancel, so the IMA is still effort over resistance. In this case, the only thing that's changing is instead of length, we get diameter, all right, which is still a length, okay? So that really doesn't change either, okay? All right, so what's the IMA of the wheel if the axle is driving the wheel? So the axle is driving, all right, so that effort is coming from the axle. All right, so the diameter of the axle is 6. So we're going to put that on the top, and then the bottom is the resistance. All right, so we're going to put 20 on the bottom, and then 6 divided by 20 equals 0.3, which is 0.3 to 1 or 3 to 10 if you move the decimal place. All right, but again, I'd leave it at 0.3 to 1 because that is, it's less than, it's less than 1, so you're inputting more force into the axle to get more turning, more distance of the turning of the wheel. Okay. Well, if the wheel is driving the axle, then you're going to invert those. You have 20 divided by 6, which is 3.33 over 1. Again, it's all simple math. You just need to plug it into your calculator. Okay. Same as before. AMA, you don't have to write this down because you already have this. AMA equals the resistance force over the effort force. All right. So we've got 270. The only thing we need to figure out is if the AMA, if the wheel is driving, then the force of the effort is going to be on the bottom, so it'll be 70 on the bottom, and the force of the resistance will be on the top, which is 200. All right, so we get 200 divided by 70. Plug it in your calculator, 2.86 to 1. All right, and then if it's backwards, and I kind of showed that one to you, all right, AMA over IMA, all right, so for efficiency, times 100, so we can take those two numbers we just calculated and stick them in the equation, and you get 85.9. Okay, and then we got the pulley. Okay, pulley is just a wheel with a groove in it. It's used to change the direction and magnitude of a force. All right, and this is important, right? We're changing the direction and the magnitude of the force. All right, so if we have an arrow that's pointing down, right? If we run it through a pulley, that arrow may be pulling up. Okay. So you can see here on this side, right? If I pulled down, if I didn't have the pulley and I pushed down with 10 pounds of force, I'm just pushing down with 10 pounds of force on this 10-pound weight. If I pull down, if I put it in a pulley, right now, right, I'm pulling down, right, it's creating an up force. Okay, so if it's a fixed pulley, first class lever, it will have an ideal mechanical advantage of 1. All right, it simply changes the direction of the force. Okay, so if I pull down here with 10, I'm going to get up 10. So it just changes the direction. If the pulley moves, all right, so in this case the pulley isn't moving. If the pulley moves, all right, you're basically creating a second class lever, okay, that has an ideal mechanical advantage of 2, right? I am pulling up with 5 pounds of force, right? In that case, I am also pulling up here with 5 pounds of force, right? Because it's not moving, it's static, right? And I'm resisting that 10 pounds force here. So what does that do for my pulley? When I pull down here 1 foot, all right, this moves 1 foot. The problem here, right, and the reason we can only exert half the force is we're moving half the distance. All right, so when you put those in the combination, all right, and you get what's called a block and tackle, you get mechanical advantage and a change of direction for effort force. And you have to like work through your brain, like, all right, this is pulling here, all right, and this is where it's then going to pull up. So if a single rope or cable is threaded multiple times through a system of pulleys, okay, so there's many different ropes through. It's one rope, right, but it goes through a bunch of pulleys. How do I get IMA, ideal mechanical advantage? So it's the number of strands opposing the force of the load. Okay, so the number of strands here. So if we look at the IMA of the pulley system on the right, right, we have 4 strands opposing the force of the load. So this is pulling down, and so this is going to pull up, 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 right? And I've only got one that's pulling down. So it's not 5 because this one's pulling down, but the rest of these are pulling up. So 4, all right, is the IMA. All right, so 4 to 1. All right. If we combine them, all right, I got a pulley here, I got a lever, right? You do the math, they're going to multiply. Okay, so I've got the number of strands here. Okay, so what's pulling up? This is pulling up, and this is pulling up. All right, so I have 2 strands times the IMA of this, right? The IMA of the pulley times the IMA of the lever. So I can go, okay, so distance of the effort, which is 2, so 12. Oh, here's the effort. So the effort being pulled up. Oh, yep, see, effort, duh. All right, so that's 12 feet divided by the 4 feet of the resistance. All right, so 2 times 12 divided by 4 is 3, so 2 times 3, so it's 6. Okay, so when you have them in combination, all right, if you have separate ropes or cables, the output of one can become the input of another. All right, this is called a compound machine, and you you have to take these carefully. So chunk it down, divide it out. So let's figure out this one. All right, I'm pulling down with 80 here. That means I'm dividing this into 40 and 40. That's pulling up, right? So that's 40 pulling up. And so in this case, I'm dividing this, right, 20 and 20 with 20 pulling up to here, and this is divided into 10 and 10. So if I pull up here with 10 pounds of force, it's in equilibrium, right? So in this case, the IMA, ideal mechanical advantage of this one, is 2, right? Because again, count the number of strands that are opposing. Ideal mechanical advantage of this is 2. Ideal mechanical advantage of this is 2, right? They're 2 opposing, all right? And then we just multiply them together, just like before. 2 times 2 times 2 is 8. So you get the ideal mechanical advantage of 8 to 1. All right. Same thing here. This one's going to be slightly tricky in that this 230 pounds is not pulling straight down, and so it can cause some problems in that you're not the horizontal vector component you're not accounting for. So that's just going to confuse things. We'll talk about that later. So AMA is the force of resistance or the force of the effort. All right, so I am resisting 800 pounds, so 800 goes on the top. The effort is 230. All right, so our actual mechanical advantage is 3.48 to 1. All right, if we want to calculate efficiency, all right, AMA over IMA, and this is the same thing we just saw before. Right, it's this one, right? So this, sorry, it's not this one, right? So the IMA, right? How many strands are resisting? 1, 2, 3, 4, and one's going down. So the 4 are going up. So IMA is 4. So multiply that out, and you get your percentage efficiency. All right, which is about 87%. Okay. This is what I was trying to talk about before. Angles do matter. It needs to be straight up or straight down. Okay. And I will try to keep it very simple for you. If the number of strands opposed to the load, only if the strands are parallel to the resistance force. Okay. So this and this are parallel. You get the IMA, right, of 2. I have 2 strands. If it's at an angle, right, you're going to have a component vertically and horizontal, right? Because this is anything that's at an angle here, right? I can convert that into a force going this way and a force going this way. Okay, and we will do that when we get the trusses. We're not there yet. Okay, so we'll use trig a little bit later in this class. All right. Um, okay. Don't make the mistake of always just counting the strands, right? If it opposes the load, um, I'm trying to think of the best way to walk you through this. All right. So number of strands opposing the load. That's IMA. Only count the strand if it opposes the load or the load's movable pulley. It might pull up or down, right? So in this case, this is pulling up, this is pulling up, or I'm sorry, this is pulling down, this is pulling down, this is pulling up. So the IMA is going to equal 2, but make certain that you're very cognizant of that. Okay, this is a lot, right? This is almost an hour-long talk that we've had. Okay, let's break it down into small chunks and work a little bit at a time. I'm going to give you some practice. We're going to talk about it in class. I know it's a lot. Okay, we will work through it together. All right. I will see you guys when we talk in class.